Thank you, and good afternoon, everyone. Yes, as David had mentioned, the subject of my talk is there, but I was going to start to follow up on a point that was made yesterday. It was a point made, and it's a valid and correct point, that before you install instrumentation, you should have a very clear idea of what you're looking for and what questions are you trying to answer. But I'll say that the information I'm going to present today really came about somewhat as a surprise to me, or it was a kind of a nice coincidence. It was not the focus of the instrumentation. I put it in for a very different reason, but upon collecting some of the initial data, I saw some interesting information that I thought warranted, informing others or sharing with others. So sometimes you get pleasant surprises with your instrumentation. In this case, I think the good thing about the instrumentation is that it's one of the rare opportunities where we could justify the cost of data loggers, so we got a more complete information than we might otherwise get, and that allowed us to delve deeper into what the data was telling us. So we're speaking about Inuvik, and so I think probably most of you know where Inuvik is, but the history is that it was a site selected in the 50s as a replacement for Aklavik. With the development going on in that area, Aklavik was constrained in terms of size of developable area, and even then there were issues in Aklavik with the nature of the permafrost and the flooding, and so a site for another sort of regional center was selected. We'll maybe at the end think about whether this was the right choice, but for now, the important thing is that it's on the edge of the Mackenzie Delta. So the objective was to get it off the Mackenzie Delta, which is, it's all continuous permafrost, but the Mackenzie Delta is particularly ice-rich. As it turns out, Inuvik is as well, but it was to get it off the Delta. That was the main point here to share, I guess. Yeah, that's probably enough for now. Now we'll talk a little bit about the geology at a kind of a high level, or simplistic geology. We're focusing on the developed area of the community, and just in general, within the developed area of the community, bedrock is fairly deep, at least for the purpose of building foundations and other infrastructure. We typically do not encounter bedrock, and so we're dealing with the soil that's there. Predominantly, the soil is, if I say clay till, I hope you know what that means, but it's soil that was laid down by the glaciers. It's primarily clay, but it's got boulders and sand mixed in with it. At Inuvik, the soil that till contains an awful lot of ice. Now, within the community, there are two areas, because the area outlined with the white hatching tends to also have a layer of, well, I say granular material, but sand and gravel over top of that till. And then towards the north, towards the east, that granular soil does not exist. It's not entirely clear at the layman's term, at the origin, but it does to me appear that there was some sort of water deposited sand and gravel, probably after the glacier, or as the glaciers were retreating, that laid down some of this granular soil on top of the till. Now, the till is ice-rich, but the gravel doesn't contain a lot of ice. Now, we'll sort of continue to set the stage a little bit. We'll eventually get you to my data, but we'll set the stage in terms of air temperature, and we've seen variations of this sort of data throughout the last couple of days. This is mean annual air temperatures at Inuvik for the period that it's been collected, so since '57, since the late 50s. So the red dots are just the average temperature for each individual year up to 2012. The blue line is what I call a 30-year moving average. So at any point on that blue line is the average of the 30 previous years. So that, since the data started in 1957, the first time you could get a 30-year average was 87. So this is reflecting basically, since that time then, the average of the previous 30 years. And I guess perhaps with the next slide, speak about why I picked that, or why I think that's a useful way to think about the data. We'll just move on to that. Okay, so now I've got the data presented in sort of three segments, with on the left being kind of the earliest data over to the most recent data. This is a summary of the air temperature data in different, and actually in fact precipitation as well. But As I indicated then, I had the moving average. So at the time that you could get your first moving average, it was almost minus 10. So this would have been in 1987. Environment Canada talks about, or sort of compiles their data in terms of normals, which are 30-year blocks of time, and they update that every 10 years. If you were to go online right now, or at least a couple months ago, the normal that you could get was up to 2000. I'm not aware that the 2010 normals are available yet. But in any case, at 2000, the average for the prior 30 years was minus 9. And as of 2012, it's minus 8. So essentially, it's telling you what the blue line told you, that you're seeing this warming in the average temperature over time. You see the same patterns in terms of freezing index, where the freezing index is decreasing, which means that you're getting less freezing over the course of a year, but the thawing index is increasing. So again, another measure of the climate getting warmer. Precipitation is reasonably flat enough that you can't really see a trend in it. I've got a couple of asterisks on the last data, and this I would like to kind of reiterate a point Heather made yesterday. You'll see that precipitation data is becoming spotty. It's not complete, and I noticed on her presentation as well, she had gaps where data was missing, and that's frustrating if you're trying to look for trends and trying to work with the data. It just makes your life difficult, and it's hard for me to understand why a place like Inuvik would not have complete data, and so it's just a bit of a side note, but I'm frustrated that we can't have complete data at a place like Inuvik. So essentially, this is saying air temperatures have been warming, at least since we've been able to sort of track the data, so since the 80s. It's not a surprise in the context of what we've been talking about over the last few days. Now I'm going to talk about ground temperature, and why I spent some time talking about air temperature is because in terms of permafrost, where you have permafrost and the nature of permafrost depends on lots of things, but I think it's fair to say, or my feeling is, that it's driven primarily by air temperature, but then after you get that primary driver, you start getting into solar radiation, you get into vegetation, you get into other things. But I spent some time on the air temperatures because to me that's the key driver for whether you have permafrost or not. This is a standard textbook illustration of a ground temperature distribution in permafrost. We don't need to get caught up in too much of the detail. We'll look at two main things. One is the active layer, and we've talked about that, and that's just that layer that freezes and thaws every year. But the one, I think, new thing that we may be talking about this afternoon is this geothermal gradient. And I think it's common knowledge that as you move deeper, the ground gets warmer. So I will call that a positive geothermal gradient. The ground gets warmer with depth. And if you, when you have complete data, this pattern is correct. That as you get close to the ground surface, you get fluctuations in the ground temperature over the course of the year. But if you average those out, it's an extension of the geothermal gradient. So this is just a generic, not to any particular scale. Now this is then an illustration of a similar plot for Inuvik. Again, this came out of a textbook. It's at a sort of a rough scale here, but it's illustrative. And even though the scale doesn't make it obvious, at least at the time this was published, and this is data, the book is from the 80s, but the data is from the 70s, it has that same slope. It's not that evident, but it has a positive geothermal gradient. And so here we're talking about in the depth range of 0 to 15 meters, which is a typical depth range that infrastructure would be concerned about. You'd be looking for foundations within that depth range. So mid-70s, all is as it should be in terms of geothermal gradient. Now, I went through several references to try and look at what the historical ground temperature characteristics were at Inuvik, starting from the late 50s when the community was developed. And because it was, let's say, an engineered community, there were some publications associated with the selection of the community site and some of the early investigations. So we look at, over the course of a couple of, or 3 decades, let's say, from the 50s to the 80s, and we have the mean annual ground temperature, minus 3.4. We have a range in this publication, but, you know, minus 3, minus 4, and then minus 3.4 again. So essentially, from the 50s to the 70s, with the limited information I could collect, we didn't see a big change in the ground temperatures in Inuvik. And during that time, there was not a big change in the air temperatures either. Active layer, we talked about active layer. It's spotty to say, I guess you could argue that the active layer is getting thinner, but it's very limited data, so don't jump to any conclusions in that regard. But certainly, we're not seeing any deepening of the active layer. I think we can agree on that. And then, because I was talking about the geothermal gradient, I didn't have it in the first I couldn't extract it from the first publication, but we have a positive geothermal gradient for through the 60s and 70s. So until the 70s, the ground temperatures are behaving as you would expect. I'm going to now kind of put a slide in that's a little out of context in terms of my understanding of the situation, but it's in kind of chronological order. So the next slide is out of a publication by Byrne, Mackay, and Coquel that they had an instrumentation at the Navy Road pit, which is well, I think of it now as a clay pit. It may have been a gravel pit at some point in time, but it's a clay pit now, basically. It's about 3.5 kilometers north of Inuvik. And so but this site was originally developed in connection with the development of the town, so in the 50s. It is a disturbed site, but it's well removed from the community. But what I want to draw your attention to in the context of what I'm about to talk about is the top part of the curve. The bottom part of the curve is doing what we expect in terms of geothermal gradient. But at the top, you've got a reverse to the geothermal gradient. And the other thing is, this is just a snippet of data because, you know, in the previous graph, I was talking down to about 15 meters. Here, the shallowest sensor's at 10. So, you know, it's pointing to something. But there's not a lot of data in the depth range where we would be interested in from terms of building infrastructure, but it's informative. So now then, with data that was collected in the 2000s, we're seeing a reverse in the geothermal gradient near the ground surface. I'll talk about that a little further in the context of my own data here. But at least I wasn't aware that this existed until after I sort of found my observations, but then this sort of corroborates it a bit. Okay, so the specific site that I have been collecting data at is the Western Arctic Research Center site, which is right near the center of Inuvik. This is one of the main intersections. The Mackenzie Hotel is here. And then the old Western Arctic Research Center is here. The new one was built in behind. This is the RCMP facility. I believe this is now called Veterans Drive, Veterans Memorial Drive, but in any case, it's the Western Arctic Research Center site, and so we put in cables. As I said, we put in cables to monitor the foundation of this building, but we had a pair of cables here, a pair of cables under the center of the building, and a pair of cables at the southwest corner of the building, and then one, what I call control. Now, I forgot to sort of say at the beginning, partly why we were doing this is there's a lot of science that's been done in terms of climate change impacts on permafrost, but a lot of it, and certainly prior to this workshop, to my knowledge, it was mostly done outside of developed communities. It was done in undisturbed terrain, and I didn't really know how to relate that to what was going on inside the developed portions of communities because conditions are different in the communities. You've got different vegetation conditions, you've got different snow distribution conditions. So this data now is allowing us to sort of look at what's going on in a community. Yeah, so that's just the location of the instrumentation. Now, this is from that control. It's got nothing to do with the building, but this is the first year of data from the control. And essentially, what I'm asking you to look at is that it's got this Again, negative gradient. The ground is getting cooler with depth. That's not what you would expect in a stable condition. This is telling you something's going on here. And then my next slide is just saying that basically we're getting the same pattern at all locations. It's, oh, sorry, let's go back. It's not that pronounced at the one location at the northeast corner of the building, and I suspect that's because the northeast corner of the new building was very close to the existing building, and I think there's probably some residual building effects going on from the previous building. But nonetheless, we're getting that same kind of gradient. Now, what that tells me, and I don't think there's any other way you can interpret it, is that when you have a geothermal gradient that's positive, warming with depth, that's telling you heat is moving from depth to the ground surface. In a cold area with permafrost, you've got a warm center of the earth, you've got a cold environment, the heat's going to go up. When you get the reverse gradient, it's telling you that heat is traveling into the ground. There's a warming from the ground surface going down. And that I have to attribute to climate change. And that's kind of why I started out by showing you what's going on with air temperatures, because to me, that's what is causing it. You could argue that it might be something to do with site disturbance, but this site was cleared back when the community, it's right, as I say, in the sort of the center of town. It was cleared back when they developed the town back in the 50s. So it's had 60 years to re-equalize. And if there wasn't some driver of warmth now, I think that that gradient in the near surface would have sorted itself out and gone back to a positive gradient, but it's still negative. So to summarize the four, essentially that. But I'm going to just do two things. One is we can talk about the gradients, but first thing I'll draw your attention to is the mean annual ground temperatures. And I had told on an earlier slide, I told you that it was running around minus 3.4. Well, now in the community at a depth below variation, we're getting 1.5 degrees. So we basically, it'll be reflected on my next slide, but we've seen 2 degrees of warming since the mid-70s to now. Active layer thickness, now I think we've got enough to suggest that perhaps there's been some increase in active layer thickness, and the gradient, and as I said, it's negative in all cases. So that tells me that it's not in a state of equilibrium, something's changing, and I believe it's influence from climate warming. So yeah, we'll just capture that in our conclusions. Mean annual air temperatures have increased about 2 degrees since the mid-70s. Until the mid-70s, there was apparently no significant impact of community development on the ground temperatures. The data seemed pretty stable till the mid-70s. Since that time, we have seen about 2 degrees warming in the ground temperature. So apparently, the ground temperature has been changing in step with the air temperature. That was something that was not immediately obvious to me. I would have thought there might have been a time lag, but at least through this range of temperatures, we've seen it sort of track in parallel. Perhaps the active layer has increased a little bit, about 0.5 meter. And then I make my conclusion about the geothermal gradient that is, it indicates that there's a heat flux now, a heat flux into the ground. And then what are the practical implications? I'll get you to think back to Steve Wolf's analogy about the ice cream yesterday. And basically, the point was that as permafrost gets warmer, it gets weaker. That has implications in terms of pile design. And so for buildings that are there, I've sort of calculated roughly, we've probably got about a 30% decrease in capacity. That's not to say buildings are failing. They're not right now, and that's because when we design things, we have all kinds of factors of safety and conservatism. But going forward, there could be a time where all those redundancies are used up and we start encountering problems. The other thing is, and it relates to a slide John had with piles jacking out of the ground, and that relates to this active layer. There's a process called frost jacking where the annual freezing and thawing of the upper soil will work on a pile and tend to lift it out of the ground. It's not as big a problem under the center of a building with heavy loads, but under things like stairways, under lightly loaded piles, that can be a problem. The response has been, as a result of the increase in active layer thickness, is that minimum pile embedments need to be increased. So that's another practical implication, is that the piles are getting longer even if they're lightly loaded, just to be able to hold them down. So that's it. Going forward, I just wanted to say that there is a guide to sort of provide guidance in terms of designing infrastructure for climate change. And it's interesting that this guide says, in the absence of modeling or better data, a good first step is to assume that ground temperature will respond in step with a change in air temperature. And that's been validated, at least by the data I have. And so that was good, because intuitively I would have suspected that was too simplistic, and I wouldn't have gone for that. But my data does seem to substantiate that sort of starting assumption or starting premise. I do have a paper on it. If you're interested in more information on this, you can contact me